Hello my friends, and welcome back to the You Can Do TV channel. Transporting and repairing a 60-ton generator demands precision engineering and strict safety measures. The massive unit was delivered on a specialized 9-axle truck trailer, built to handle extreme loads with stability. Upon arrival, unloading required partial disassembly, beginning with the careful separation of the rotor from the stator. This critical step minimized weight and allowed safer handling during lifting operations. Two cranes worked in perfect coordination to raise the rotor, with operators maintaining constant communication to avoid imbalance or structural stress. Once lifted, the rotor was slowly maneuvered and secured in a designated temporary storage area, ensuring protection before inspection and repair. The remaining stator components were then prepared for further servicing. Such operations highlight the complexity of handling large-scale power generation equipment, where logistics, heavy lifting, and technical expertise must align seamlessly. Every stage, from transport to rotor removal, demonstrates the demanding process required to restore a generator of this magnitude. Electric motor maintenance demands both technical precision and strong teamwork. Each stage begins with coordinated disassembly, where technicians carefully handle heavy components using cranes and lifting equipment. Specialists inspect windings, bearings, and insulation, while engineers conduct electrical testing to identify faults. Rewinding crews, insulation experts, and machinists work in sequence, ensuring mechanical integrity and electrical reliability. Communication between departments, from diagnostics to final assembly, keeps operations efficient and error-free. Once reassembled, the motor undergoes rigorous performance testing. This collaborative effort ensures durability, minimizes downtime, and delivers dependable power, proving that successful motor maintenance is built on skill, discipline, and teamwork. Working with a 50-foot lathe brings immense capability to heavy industrial machining. With a 10-foot 4-jaw chuck, 12-foot swing, and 50 feet between centers, the lathe holds a .0005 taper within 3 feet, powered by a DC variable speed drive for precision control. Among its impressive tasks is machining the massive armature of a 9,000 HP motor, critical for automobile shredding operations where durability and accuracy are paramount. At Pearl Harbor, the lathe produced a stationary runner for a dewatering pump, ensuring reliability in demanding marine conditions. It also machines brass wear rings, where fine tolerances are essential to minimize friction and extend service life. Another achievement is finishing a 10-foot diameter generator armature, a component requiring flawless balance and structural integrity. These projects highlight the lathe's unmatched role in supporting power generation, naval infrastructure, and heavy industry. When a massive impeller spins at high speed, even the slightest imbalance can turn smooth power into destructive vibration. Balancing is the art of restoring harmony to this rotating giant. The process begins with a baseline analysis, measuring the repaired impeller's natural vibration profile. Sensitive sensors detect every irregular shake, providing the data needed to begin correction. Temporary calibration weights are then applied, with a simple sheet of paper attached to the impeller's outer rim to reduce air interference during testing. After calibration, permanent metal balance weights are installed and precisely adjusted. Multiple cycles of measurement and correction follow until the vibration levels fall within safe operating limits. Once balance is achieved, the impeller is ready to run smoothly, protecting the machinery it drives and extending its service life. Motors up to 5,000 HP are tested at 600 RPM, and 4,000 volts. The system monitors voltage, current, speed, winding temperature, vibration, and operational performance. Rewinding a 550 horsepower large electric motor demands a highly controlled and methodical process to restore efficiency and extend operational life. At Koffler's full-service repair facility, the procedure begins with a complete disassembly of the motor to access its critical internal components. The rotor is the first focus. It undergoes precision banding to reinforce structural integrity, followed by balancing operations. Both pre-balancing and post-balancing checks are performed to ensure smooth, vibration-free operation during high-speed performance. Attention then shifts to the stator, which is carefully stripped of its damaged windings. Skilled technicians rewind the stator with new copper coils engineered for optimum conductivity and durability. To secure long-term insulation, the stator is subjected to vacuum pressure impregnation, VPI. During this process, insulating resin is forced deep into the windings under vacuum and pressure, creating a protective barrier against moisture, electrical stress, and environmental degradation. This stage significantly improves dielectric strength and enhances the overall reliability of the motor. Once rewinding and insulation are complete, the motor enters the reassembly phase. The stationary runner is accurately installed and aligned to ensure proper mechanical interaction with the rotor. Every component is rechecked before final closure of the motor housing. Comprehensive testing follows, including voltage verification, insulation resistance measurement, and load performance assessment. These rigorous tests confirm that the motor meets or exceeds performance standards. All results are fully documented, and the motor is certified prior to shipment. In this specific case, the rewound motor was prepared for maintenance of a dewatering pump impeller at a submarine dry dock in Pearl Harbor, where reliability is critical. From rotor banding to VPI treatment and final certification, the process demonstrates precision engineering and expert execution in large-scale motor restoration. In KOFFLER's full-service shop, motor rewinding and rebuilding unfolds with exacting precision and technical expertise. A large, slow-speed vertical water pump motor is carefully disassembled, exposing the intricate components that power industrial operations. The facility services AC and DC motors of all sizes, including high-capacity units such as a 5,000 kilowatts wound rotor. Advanced techniques are employed. Random winding of multiple strand stator coils, layer winding for rotating field coils, and careful reassembly of exciter rotors. Laminations are replaced when necessary, as in a 500 kilowatts generator, while DC armatures are prepared, insulated, and reassembled with layer-wound pole pieces using rectangular wire. Connections are meticulously made on main DC field motor generator sets, and coils are inserted and wedged to ensure structural integrity. Completed stators undergo rigorous output voltage testing to confirm balanced three-phase performance. Each step ensures mechanical precision, electrical integrity, and reliable performance in demanding industrial applications. The construction of the sail training ship Union by SEMA Peru represents a major milestone in naval engineering and maritime education. This tall ship is designed as a platform for training future naval officers, while also serving as a symbol of Peru's maritime heritage and technological capability. The project combines traditional sailing architecture with modern engineering techniques, ensuring that the vessel is fully operational, safe, and capable of long-range ocean navigation. All of the 38 total structural modules of the ship have been completed. These modules include the accommodation areas, the engineering plant, and the double bottom sections, which provide essential structural strength and stability. An additional 9 blocks, corresponding to the stern and central deck sections, are currently under construction and assembly. Each module is fabricated with high-precision welding techniques, ensuring dimensional accuracy and structural integrity. The assembly of these blocks requires meticulous alignment to guarantee a seamless integration of hull sections, decks, and bulkheads. Inside the installed modules, approximately 70% of the machinery and equipment for the engine room has already been installed. This includes the main engines, diesel generators, and climate control systems. The careful placement of these systems follows strict naval engineering standards to optimize performance, efficiency, and accessibility for maintenance. Installing heavy equipment within partially assembled modules presents logistical challenges, requiring coordinated lifting, alignment, and securing to avoid structural strain. The hull construction is executed with a modular approach, which allows simultaneous work on multiple sections. This technique enhances construction efficiency while maintaining strict quality control. Each steel module is fabricated with reinforced plates and internal support structures to withstand stresses encountered during sailing and rough seas. Welding quality, material thickness, and alignment are continuously inspected, ensuring the vessel meets both national and international maritime safety standards. The rigging and sail system is another critical component of the Union. The vessel features 4 masts and a total sail area exceeding 400 square meters. Masts and spars are carefully aligned, and the standing rigging, including shrouds, stays, and turnbuckles, is installed to provide structural support under full sail. The ship's engineering systems integrate modern navigation, communication, and safety technologies. Electrical systems, plumbing, HVAC, and auxiliary machinery are installed in a manner that allows cadets and crew to operate and maintain the equipment effectively. Training areas, classrooms, and living quarters are designed to maximize functionality without compromising the vessel's structural integrity or safety. The modular construction method allows for systematic installation and testing of all onboard systems, ensuring that every component is fully operational before the ship's launch. Throughout construction, SEMA Peru has maintained rigorous project management, coordinating teams of engineers, welders, riggers, and technicians. This collaboration blends traditional shipbuilding craftsmanship with modern engineering and precision technology. The modular approach, combined with strict quality control, allows simultaneous progress on hull fabrication, machinery installation, and interior outfitting. When fully completed, this three-masted sail training ship stretches 115 meters long with a 13-meter beam, blending the elegance of classic sailing with modern steel hull technology. Every detail, from the cadet classrooms to the living quarters, has been meticulously crafted to provide hands-on naval training. Modular blocks were precisely assembled at the SEMA shipyard, ensuring unmatched durability and safety at sea. The Union will serve not only as a training platform but also as a maritime ambassador. Cadets will gain hands-on experience in navigation, seamanship, leadership, and teamwork. The vessel will also represent Peru in international events, fostering diplomatic and cultural relations. In summary, the construction of the Sail Training Ship Union by SEMA Peru exemplifies a harmonious integration of naval tradition and modern engineering. The construction of the multipurpose ship BAP Pisco at SEMA Callao has successfully completed its first stage, from keel laying to launch. The project involves coordinated fabrication and assembly of steel modules, each meticulously processed in workshops for structural integrity, alignment, and durability. Naval construction workshops handled hull plates and framing, while specialized teams installed piping, valves, and electrical systems. Painting, surface treatment, and corrosion protection were executed with precision to ensure long-term performance. The engine room installation has progressed with careful placement of diesel engines, generators, and climate control systems, integrating modern propulsion and auxiliary machinery. Systems are arranged to allow safe operation, maintenance, and accessibility, adhering to naval engineering standards. Production planning and quality control teams monitored every step, ensuring compliance with design specifications, welding quality, and alignment tolerances. Project leaders highlighted the collaborative effort across logistics, design, planning, and production areas, emphasizing technical expertise and hands-on problem-solving. Each module was tested individually before integration, and specialized equipment ensured accurate lifting, positioning, and joining. The vessel, now ready for outfitting and sea trials, will provide the Peruvian Navy with versatile operational capability. The project demonstrates advanced shipbuilding techniques, efficient modular assembly, and comprehensive system integration, reflecting SIMA's commitment to engineering excellence. BAP Pisco embodies a combination of precision, durability, and innovation, ensuring it meets functional requirements while serving as a platform for national maritime operations. The BAP Union, the largest sailing school ship in Latin America, stands as a milestone in Peru's naval history. Built at the Cima shipyards with more than 25 years of accumulated expertise, the vessel was designed entirely with Peruvian engineering and craftsmanship. Constructed with thousands of tons of naval steel, it reflects the skill of both naval officers and civilian workers who turned vision into reality. During the baptism and launch ceremony, blessings were invoked for the ship and its crew, marking the start of a mission that extends beyond training, carrying the Peruvian flag proudly across oceans as a floating embassy of culture, diplomacy, and national pride. The christening and launch of the multi-purpose ship BAP Paida highlight Peru's growing naval industry. Built entirely with Peruvian expertise at Cima, its construction used more than 5,000 tons of naval steel and created around 500 jobs. The Paida measures over 120 meters in length, displaces approximately 11,000 tons, and reaches speeds of 16 knots. Designed to transport troops, armored vehicles, containers, and humanitarian cargo, it also supports amphibious operations with modern cargo handling and landing systems. Beyond military tasks, the vessel plays a vital role in disaster relief, logistics, and peacekeeping missions, strengthening national defense and regional cooperation. The christening and launch ceremony of the training ship BAP Union marked a historic moment for Peru. Held on December 22, 2014, at Servicios Industriales de la Marina S.A., the event was graced by President Ollanta Humala Tasso, Minister of Defense Pedro Cateriano Bellido, and Admiral Carlos Tejada Mera. As the majestic hull touched the water for the first time, pride and emotion filled the air, a symbol of Peru's maritime spirit, craftsmanship, and national unity. Between June 1 and August 31, 2014, a major railway modernization project was undertaken that involved dismantling and rebuilding 11.9 kilometers of track. The process began with the careful removal of existing rails, sleepers, and ballast. Old track components were disassembled using specialized track lifting and cutting equipment, ensuring that reusable steel elements could be recovered for later use. Once the old materials were cleared, the subgrade was inspected and stabilized to provide a durable foundation for the new infrastructure. Track rebuilding commenced with the placement of a fresh ballast layer, distributed and leveled by high-capacity ballast regulators. Concrete sleepers were systematically positioned at precise intervals to guarantee stability and alignment. New rails were laid, aligned, and joined through advanced welding techniques, creating seamless track segments that enhance performance and reduce maintenance requirements. Mechanical tamping machines then compacted the ballast around sleepers, securing geometry and ensuring correct track gauge. In September, attention shifted to the reconstruction of the Rakonievsky station. Work included the renewal of station tracks, switches, and drainage systems, as well as the upgrading of service platforms and operational facilities. This modernization aimed to improve safety, operational reliability, and passenger comfort. By the end of November, drainage ditches along the rebuilt track were restored to ensure effective water management, preventing subgrade erosion and prolonging infrastructure life. A service shelf adjacent to the track was also reconstructed, facilitating inspections and maintenance activities. Additionally, all recovered railway materials deemed reusable were sorted, prepared, and handed over for secondary use, contributing to cost efficiency and sustainability. The project not only restored critical rail infrastructure but also improved long-term reliability, ensuring that both passenger and freight services could operate with greater safety and efficiency. Lithuania's railway network is being renewed with the help of advanced technologies and modern construction methods. In 2019 alone, Lietuvos geležinkeliai repaired and upgraded over 83 kilometers of main railway lines, investing €30.4 million, 30% more than the previous year. This work is part of a long-term 2014 to 2024 plan that dedicates €247 million to modernize or replace 640 kilometers of track, almost one-third of the national system. Specialized track-laying machines, tamping units, and ballast regulators are employed to ensure precise alignment and stability. Welding technologies are used to create seamless rails, while heavy-duty cranes and mechanized systems replace old sleepers and install new components efficiently. With a managed network of 2,000 kilometers, such equipment allows crews to complete projects faster while minimizing disruption to train traffic. Looking ahead, €40 million will be invested annually to renew about 80 kilometers of track per year. These upgrades already show results. Speed restrictions were reduced fourfold, contact line failures decreased, and service reliability improved significantly. By combining investment, skilled specialists, and advanced machinery, Lithuania's railway infrastructure is steadily increasing in safety, efficiency, and long-term value. Etihad rail sleepers are built locally, yet meet the highest global standards. Each pre-stressed concrete element is 2.6 meters long, weighs 340 kilograms, and ensures track stability by locking rails in place and transferring loads safely to the ballast below. Inside the factory, the long-line method produces up to 200 sleepers per casting. From mold preparation and wire tensioning to steam curing and rigorous quality tests, every step guarantees strength, precision, and long-lasting performance. Railway modernization is a vital process for ensuring safe and reliable transport. On a key section of track maintained by Deutsche Bahn, the replacement of worn sleepers and rails was carried out using advanced mechanized systems. The Salov 315 track renewal machine plays a central role in this operation, capable of lifting rails, extracting old sleepers, and positioning new ones in a continuous sequence. This highly efficient method minimizes service interruptions while extending the life cycle of the railway infrastructure. The project demonstrates how precision machinery sustains the performance of Germany's rail network. The URM 700-2, a revolutionary multi-talent machine transforming ballast cleaning, with unmatched efficiency and precision. Designed to operate continuously through turnouts, it eliminates the need for full track closures and excels in short track possessions, requiring only an 8-meter construction gap. At the front, material is removed from the shoulder, while the infinitely adjustable excavating sword allows precise control over excavation width. A trough scraper collects and conveys material efficiently, and advanced track lifting and holding devices ensure safe, accurate alignment throughout the operation. Ballasting is performed in 2 stages, tamping zones at the front and variable ballast distribution at the rear, covering the entire width of the ballast bed. The vibrating screening unit thoroughly cleans the ballast, separating spoil from reusable material. Spoil is transported via conveyor systems to hopper units, while fresh ballast is simultaneously inserted to maintain a continuous workflow. The URM 700-2 combines precision engineering, flexibility, and operational efficiency, making it indispensable for modern railway maintenance and trackbed management. At the IAF 2025, Goldschmidt demonstrated its advanced Thermite head repair (THR) welding process, designed to restore railhead defects without cutting or neutralizing the track. Preparation began with precision oxy-fuel cutting to remove surface irregularities, such as squats, shelling, or cracks. A specially designed mold, incorporating a felt seal that expands during preheating, was then applied to ensure complete containment. Preheating was achieved using the jet system, a compact battery-powered propane tool requiring no oxygen supply. Once at temperature, the aluminothermic reaction was initiated, depositing fresh steel into the groove. Environmental considerations were addressed through a new filtration system, capable of reducing emissions by up to 99%. Following solidification, the UC4 Plus S shear removed excess material, also battery-powered for efficiency. Final grinding was carried out with the MP6 retrofit system, enabling 6 welds per charge. This standardized and portable method now supports rail grades R260 and R350, ensuring durable, precise, and sustainable rail repair. Traditional track dismantling with the case Poclane excavator showcases the classic method of railway removal. Step by step, hydraulic power lifts and separates rails and sleepers with controlled precision. This process ensures safe clearing of the line, paving the way for maintenance, replacement, or complete modernization of railway infrastructure. On the Great Central Railway, locomotive 78018 operates in live steam between Quorn and Loughborough, demonstrating classic British steam engineering. The engine's boiler pressure, valve gear, and cylinder mechanics work in perfect harmony to drive its wheels along the preserved mainline. Steam exhaust and motion linkages are visible, illustrating mechanical efficiency and precision. This operation highlights the intricate engineering of heritage locomotives, showcasing both power and craftsmanship in authentic running conditions. The production of steel rails at Trenecce Zelezarny represents a combination of metallurgical precision and engineering excellence. High-quality steel is smelted, continuously cast, and hot-rolled into durable rails designed to meet demanding performance standards. Advanced heat treatment processes improve hardness, wear resistance, and dimensional stability, ensuring long service life in heavy-duty applications. Steel rails are deployed in diverse European projects. City rail systems in Oslo, Norway, where vibration resistance and passenger comfort are critical. Urban rail infrastructure around Hengelo and Groningen in the Netherlands, requiring durability in high-traffic commuter zones. And specialized switch rails in Zermatt, Switzerland, engineered to withstand extreme alpine conditions. Each application demonstrates the versatility of steel rails, reinforcing their reputation as a trusted solution for modern, safe, and sustainable railway networks. Saarstahl Rail manufactures high-quality rails from low-carbon dioxide electric arc steel, supporting sustainable mobility solutions. Raw blooms, produced in Saint-Sever, are delivered mainly by rail, stored and reheated in gas furnaces to the optimal rolling temperature. Rolling begins with reversible roughing stands, where blooms undergo 8 to 12 passes to form rail blanks. Subsequent stages use the universal rolling process in 6 stands, with the final pass imprinting identification marks, as required by international standards. Rails are then cooled in a controlled manner on cooling beds, incorporating horizontal bending to minimize distortion and achieve straightness. Precision is ensured by roller straightening machines correcting both vertical and horizontal planes. Advanced non-destructive testing follows, including ultrasonic inspection, dimensional checks, and surface control. Finished rails, up to 100 meters long, are dispatched to major rail networks across Europe. Railways play a vital role in modern infrastructure. They provide safe, efficient, and high-capacity transportation for both freight and passengers. By reducing road congestion, rail lowers accidents and logistics costs. Environmentally, it cuts carbon emissions compared to trucks. Strategically, rail enhances regional connectivity, supports trade growth, and drives sustainable economic development. A rail welding plant is a specialized facility designed to join short rail sections into longer continuous lengths, ensuring smooth, safe, and durable railway tracks. The operation starts with short rails handling and feeding, where rail segments are carefully positioned for welding. Next, the Geismar Bra 32 system performs precise cleaning of rail ends and sections, preparing them for a high-quality joint. The heart of the plant is the flash butt welder, which fuses the rails together with controlled heat and pressure. Pinch rollers guide the welded rails, while the weld testing press ensures the bond meets strict strength standards. Any misalignments are corrected using the Geismar PHR 250120 four-way weld straightening machine, followed by finishing with an automatic weld grinder for perfect surface quality. For efficiency and safety, the plant integrates Geismar fixed gantries, storage, and handling systems. With tailored layout and process engineering, rail welding plants deliver optimized productivity and reliable rail infrastructure for modern transportation networks. A new chapter in Russian rail production has begun, with Evraz unveiling the country's first 100-meter rails. This breakthrough, achieved after a large-scale modernization project worth over 18 billion rubles, places Russia among the global leaders in advanced rail manufacturing. With a design capacity of 950,000 tons per year, the facility combines innovation, precision, and strict quality control. Rail billets, cast in the steelmaking shop, are heated and rolled into exact profiles before being stretched to full length. Each rail is assigned an electronic passport, ensuring complete traceability. A state-of-the-art air hardening installation enhances the railhead's durability while preserving ductility, vital for heavy-duty applications. After controlled cooling and straightening, rails undergo ultrasonic and eddy current inspection to confirm geometry, alignment, and defect-free surfaces. The result is a new generation of rails with superior strength and straightness, certified for high-speed railway lines operating at up to 350 km per hour. How do railways ensure absolute safety when guiding trains through complex turnouts? Rail systems clamp lock point machines, drive, lock, and detect switch rails on turnouts and crossings. A hydraulic cylinder activates rams that move slides and lock arms, securing rails in open or closed states. With microswitch detection, compact installation, and optional in-bearer design, it ensures reliability, safety, and efficient signaling integration, even in confined rail environments. In steel plants, hydraulic cylinders play a critical role in maintaining precision and reliability across demanding operations. AGC cylinders ensure accurate thickness control during rolling, while shift cylinders handle precise roll adjustments and positioning. For electric arc furnaces, continuous casting machines, and bending systems, cylinders are engineered to withstand extreme heat, high pressure, and heavy loads. Manufactured with tight tolerances and robust materials, they deliver stability and consistent performance. Their integration into mill systems ensures smooth operation, reduced downtime, and long-term durability under the harshest working conditions. Winter brings unique challenges to railway operations, and LTG Infra ensures safety through specialized snow clearing technology. After several years, the powerful Snowplow train returned to service, designed to tackle snow layers up to 0.8 meters thick across stations and access tracks. This massive machine, weighing 180 tons, consists of a leading unit, 2 intermediate wagons, and a rear wagon, all operated by 3 skilled drivers. With the ability to collect up to 350 cubic meters of snow, it keeps Lithuania's railways clear and reliable even in harsh conditions. The completion of Etihad Rail's 9 tunnels across Fujairah and Ras Al Khaimah marks a historic milestone for the UAE. Behind this achievement lies the dedication of countless men and women who faced immense challenges with courage, teamwork, and determination. Through rocky mountains and harsh conditions, they dug not just tunnels, but a path toward progress and unity. This is more than an engineering triumph. It's a story of perseverance, pride, and the spirit of a nation moving forward together. Carved through the heart of the Hajar Mountains, Etihad Rail has completed excavation of the Gulf's longest rail tunnel, a 1.8-kilometer engineering landmark. As part of Package D, Stage 2 of the UAE National Rail Network, the project demanded world-leading technology to overcome complex geology and guarantee structural stability. Precision blasting, reinforced lining, and continuous monitoring guided the process with safety at its core. One of 9 tunnels in this phase, it not only enhances connectivity across the region, but also stands as a symbol of innovation, resilience, and the UAE's vision for sustainable rail transport. Production of pre-stressed concrete sleepers at Leonhard Mall using Vollert and Lagenbau-influenced technology is a high-volume, precisely controlled industrial process designed to meet rigorous standards for durability, safety, and performance. Leonhard Mall produces well over 1 million reinforced concrete sleepers per year, supplied to major rail operators across Europe. Mixing and preparation of the concrete is an early stripping process with relatively dry concrete mixes. Advanced DI-RIC mixing technology, ring trough and planetary mixers, are used at the Biebesheim plant to achieve high tool speeds and intense shear forces in the mix. This ensures uniform distribution of cement and moisture, delivering concrete that is homogeneous and stable, even very early on after casting. Once freshly mixed, concrete is fed into molds, reinforcement cages, steel reinforcement frames, are prepared beforehand and placed into molds according to sleeper design. Concrete is poured into molds with automated distribution systems, often using conveyors, feeders, and silence-isolated casting chambers. Vibration or compaction systems remove air voids, ensuring density and strength. Early stripping of molds is applied, meaning that molds are released relatively soon after casting, benefiting from the strong dry mix to allow safe demolding without damage. This increases throughput and mold reuse. Curing is conducted in specialized chambers under controlled temperature and humidity. Steam or heat aging may be used to accelerate strength gain to required structural performance. Sleepers are then demolded with lifting equipment, and finished processes follow, including trimming of edges, applying identification markings, factory mark, year, rail foot width classification, on sleeper heads and rail seats. Dimensional and strength testing is integral. Laser or sensor-based measurement systems check length, width, rail foot geometry, rail seat surface, and other critical tolerances. Sleepers must meet standards such as DIN EN 13230 and Deutsche Bahn specifications, DBS 918143. After passing quality checks, sleepers are stored, packaged, and dispatched via road or rail. Logistics involve special handling equipment. Sleeper grippers, traverses, trolleys, and block trains are used to transport large volumes safely and efficiently. The Leonhard-Moll process, combining high-performance dry mixing, early stripping, precise reinforcement, rigorous curing, and tight quality control, renders concrete sleepers with excellent load-bearing capacity, long service life, and consistent performance under heavy traffic and challenging environmental conditions. The ICF system uses prefabricated insulating panels and rebars inside the slabs assembled as formwork, then reinforced concrete is poured inside. The finished structure is durable, provides excellent thermal and acoustic insulation, saves energy, and significantly accelerates the overall construction process. The UAE's first marine rail bridge spans 1 kilometer, linking Khalifa Port with the UAE National Rail Network. Built under Stage 2, Package B of Etihad Rail, the bridge features 100 T-beams, 18 300 cubic meters of reinforced concrete, and 4 117 tons of steel. It parallels an existing road bridge to maintain water flow and protect coral reefs in the Arabian Gulf. Designed for freight transport, each fully loaded train crossing the bridge is expected to remove up to 300 trucks from UAE roads. When concrete meets its strongest partner, the result is MST bar, a fiberglass structural rebar redefining modern construction. Designed in Canada and approved across North America, this innovation combines strength, lightness, and durability in one solution. Non-corrosive, non-conductive, and 75% lighter than steel, it makes transportation, handling, and installation safer and more efficient. Yet MST bar is over 3 times stronger than steel, using continuous glass fiber strands and an integrated rib profile that bonds securely with concrete. Contractors benefit from easy on-site cutting without sparks or debris, while pre-bent bars arrive ready for complex details. Meeting standards, MST bar is already proving its value in bridges, condos, and multi-story projects. In modern construction, the choice between FRP rebar and steel rebar defines long-term performance. Steel offers proven strength, but suffers from corrosion, heavy weight, and costly maintenance. FRP rebar, lighter and 20% stronger in tensile capacity, delivers corrosion resistance, chemical durability, and reduced handling costs, making it the superior alternative. The production of GFRP rebar follows a precise technical process to ensure maximum strength and durability. First, continuous glass fiber rovings are prepared and degreased for proper bonding. These fibers are then impregnated with specially formulated resin, ensuring complete saturation and removal of air pockets. Next, the resin-soaked fibers are pulled through shaping dies, where ribs are formed to enhance concrete adhesion. The profile enters a controlled polymerization chamber, curing uniformly from the inside out. After curing, bars are gradually cooled to prevent thermal stress, then cut to length or coiled. Finally, strict quality control verifies tensile strength, dimensions, and bonding performance. A breakthrough in composite reinforcement technology has been achieved with a line that produces 6 GFRP rebars simultaneously. Using advanced pultrusion, multiple fiberglass strands are drawn, impregnated with resin, and cured in parallel channels, creating 6 perfectly uniform rebars in one continuous cycle. The line integrates optimized heating and resin impregnation systems, enabling flawless bonding of fiberglass strands within the polymer matrix. Energy efficiency is enhanced through smart power management, reducing overall consumption without compromising output quality. Automated cutting and sizing units guarantee dimensional accuracy, while the continuous process minimizes downtime and manual intervention. With the ability to multiply productivity 6-fold, this system not only boosts manufacturing capacity, but also ensures each rebar meets stringent structural performance standards required in modern construction applications. FRP rebar offers superior strength, corrosion resistance, and lightweight handling, making it ideal for highways, bridges, airports, docks, and underground projects. When produced to strict quality standards, it effectively replaces traditional steel reinforcement in complex construction environments. Mesh rebar, produced with precision using composite tech equipment, delivers unmatched rupture, breaking, and tensile strength. Recognized by construction experts worldwide, it ensures lightweight durability, corrosion resistance, and long-lasting performance in modern infrastructure projects, setting a new benchmark in structural reinforcement. Every 2,000 hours of operation, the pedestal crane undergoes a complete maintenance cycle. Starting with the electric motor, it is dismantled and cleaned. Next, the gearboxes for hoist and slew are inspected, with oil drained and replaced. The slewing system is serviced, bearings lubricated, bolts checked and tightened. Moving to the hoist drum, all pins, bearings, and cables are lubricated. The load handling system is carefully examined, ensuring hook safety and sheave condition. The hydraulic unit is flushed and refilled, while the electrical system is inspected and cleaned. Attention then shifts to the cabin for visibility and safety, followed by thorough brake maintenance. Finally, the crane is tested, inspected, and officially handed back for safe operation,